Have you ever wondered what exactly energy quantization is and what can one understand from this branch of quantum physics? I'll be helping you to understand what energy quantization is, what there is to know about it, the theories that build it up and so on. Be sure to subscribe and pause the video to get your jotters ready. Let's start our new topic. Some of the important postulates of the Bohr's model of the atom was that the electrons moved around the nucleus in specific orbits. In these orbits, they can move without radiating energy. They can acquire or lose energy only in discrete units called quanta. Thus, Bohr suggests that electrons in the atom exist in discrete or quantized energy states. In 1902, Max Planck was able to show that experiment observations in the radiation emitted by substances could be explained on the basis that the energy from such bodies is emitted in separate or discrete packets of energy known as energy quanta of value hf, where f is the frequency of radiation and h is a constant known as Planck's constant. Thus, the energy E of one quantum of radiation of photon is given by E equals to hf. This is known as Planck's theory of radiation. The term quantum means fixed amounts or discrete or separate amounts as distinguished from a continuous quantity. Planck's quantum hypothesis thus suggests that the energy of radiation can be E equals to hf or 2hf or 3hf and so on, but they cannot be vibrations or radiations whose energy lies between these values. That is, energy radiated is not a continuous quantity, but rather quantized, meaning it exists only in discrete amounts. This is the meaning of the concept of energy quantization. Electrons in atoms are believed to be arranged around their nuclei in positions known as energy levels, or electron orbits or electron shells, anyone you wish to call it. The electron is held in its orbit by the force of attraction between it and the nucleus. Each electron in a given atom possesses a specified amount of energy that is related to the distance between the electron and the nucleus. Since the electrons in an atom are restricted to individual orbits, they are said to occupy energy levels. Electrons in the orbit closest to the nucleus have the highest energy, meaning it takes more energy to remove such electrons from the first energy level than to remove electrons from any of the other higher levels. Such electrons in the closest orbit to the nucleus are said to be in the ground state or lowest energy level. The energy of an electron is given by the relation E equals to minus 1 over n squared multiplied by r, where n is the electron's quantum number and r is a constant. The minus sign signifies that one must do work on the electron to remove it from the atom. When an atom is heated or bombarded with an energetic particle, its energy is increased and the atom is said to be excited. For the atom to be excited, its energy must be increased by a definite amount. No intermediate energy change is possible. During excitation, which is the process of increasing the energy of the atom, one or more of the atomic electrons may move to a higher energy level. The electron possesses this higher energy as long as it remains in the excited state. Because excited states are unstable, the electron soon jumps back to its original orbital energy level and emits a photon or quantum of light with a characteristic frequency f or wavelength lambda in the process. According to the relation, E subscript n minus E subscript 0 equals to hf subscript n equals to hc over lambda subscript n, where E subscript n is the energy in the excited state and E subscript 0 is the energy in the ground state. An ordinary tube of hydrogen or any other gas does not give off light. The gas can give off light only if energy is first given to the atoms of the gas. A gas atom giving energy is said to be excited. A gas atom can be excited or energized either by heating or by sending an electric discharge through the gas. Electric discharge through the gas can be made by placing a high voltage across a tube containing the gas at low pressure. When the gas atoms are excited, they give off light which when analyzed is seen to consist of a large number of spectral lines. Each line consists of light of one wavelength or color. The This type of spectrum is called a line spectrum, or the atomic spectrum of the elements. A line spectrum is a spectrum that consists of a number of well-defined lines, each having a particular frequency or wavelength or color. A continuous spectrum, on the other hand, consists of light of all colors or wavelengths. When light falls on metal surfaces, electrons are emitted. This is the photoelectric effect. The emitted electrons are known as photoelectrons. A puzzling feature of this phenomenon was as first discovered by Leonard in 1902 was that of maximum kinetic energy of the emitted electrons was independent of the intensity of the incident light, but was proportional to its frequency or wavelength. In 1909, Einstein proposed an explanation of the photoelectric effect using a concept first put forward by Max Planck, that light waves consist of tiny bundles or packets of energy known as photons or quanta. Each photon of light or electromagnetic wave has an energy hf, where h is Planck's constant, which is equals to 6.62 times 10 raised to the power of minus 34 joules second, and f is the frequency of the light. Einstein's idea can be expressed in the equation hf equals to w plus 1/2 multiplied by mv squared. The term hf represents the total energy content of a single photon of incident light. Part of this energy, W, is used to get the electron free from the atom and away from the metal surface. This energy W is known as the work function. The remainder of the energy is used to give the liberated electron a kinetic energy 1/2 multiplied by mv squared, where v is the velocity of the photoelectron of mass m. W is different for different metals. The work function W is given by W equals to hf subscript 0, where f subscript 0 is the threshold frequency. The threshold frequency is the frequency of light which, when falling on a surface, is just sufficient to liberate electrons without giving them any additional kinetic energy. The work function W of a metal is the minimum energy required to liberate an electron from a metal surface. From the equations put forth before, we can combine them to obtain the equation hf equals to hf subscript 0 plus 1/2 mv squared, where hf subscript 0 is the work function. We can now turn 1/2 multiplied by mv squared equals to capital E. Now we will now have hf equals to hf naught plus capital E. Now, when making capital E solid of the formula, we will now have E equals to hf minus hf subscript 0. This is Einstein's photoelectric equation. The energy of the ejected electron may be found by determining what potential difference V must be applied to stop its motion. Therefore, E will now be equals to 1/2 mv squared equals to small e multiplied by capital V. The product EV is known as the electron volts, which is equivalent to 1.6 times 10 raised to the power of minus 19 joules. Hence, we can write the equation as capital E equals to EV equals to hf minus hf subscript 0. For any surface, the incident light must be of short enough wavelength or high enough frequency so that the photon has enough energy hf to eject the electron. Applications of photocells are in photometers, burglar alarms, automatic doors, television cameras, and sound production from film tracks. I will advise, if you didn't quite grab everything in this video, be sure to rewatch and go through what you have jotted down, and I'm sure you'll get it right. Thanks for watching, and I hope we learn more together.